All right, let's take a look at exercise 8.3, which is our final problem from our chapter 8 problem set. And so here we're told we have a system of 10 equations with 10 unknowns. So it's a system of 10 linear equations. So they're linear, so I'm going to solve using rref. And so we have our system of equations, then also the solution. Now, before I even jump over to MATLAB to solve, so I can write say a function with no inputs or a script to solve this one. We'll use rref, and as I set it up, half the problem is going to be just typing. So when I solve using rref, I'm going to write a matrix of my coefficients, if you will, exactly as I have here. So this first equation is every term. So I'm going to end up with a matrix which has 10 rows, right, one for each column, and or one for each equation, 10 rows and 11 columns, one for the coefficient in front of each variable, which is here x subscript 1 through 10. And then the 11th column is for what that equation is equal to, so the right-hand side of my equality. And so most of the problem here is going to be typing. So let me start by writing a script, and then we could always wrap it up in a function if need be. And yeah, so start with our equation of coefficients. And I'm just going to make a note that it's going to look as a comment. Okay, that this is going to look something like, the term in front of x1, x2. Sorry, my x2, comma, x3, comma, dot, 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 comma, x10, and then comma, and I'll just write like the right-hand side of my equation. All right, so let me just make this say vector A. Okay, and then the nice thing is as long as I keep my brackets open, okay, return's going to mean a new line. And so let me try and write down or type up my matrix. And my apologies, this could be pretty boring. Right, I wish I could copy a little better, but let's try. If I just copy and paste, I don't think, well, maybe I can roll with this. Okay, so if I copy and paste, the issue is I have all of these variable terms. I guess I could do this, right? So let me just, I'm trying. This is different than what we did in class. And maybe it's easier. Okay, so let me delete all these variable terms. Okay, the first had all 11, right? And then I delete the equal sign. So first is, and I'd have to delete the plus as well. Yeah, maybe this isn't any easier. All right, because there's x1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the right-hand side of my equality. Let me put a couple extra spaces in here. Okay, and so if I try and line up my second, so the second term just has x2, so it has 0 for x1. Okay, let me start with x2, x3. I need to delete the plus sign. Excuse me. x3, x4, x5, 6, 7, 8, 9, and 10. Okay, delete the plus sign, delete the plus sign, delete the plus, right? And we can keep lining up. Okay, whether or not this is best, well, let's see. So it's x1, 2, 3, 4, 5, 6, 7, 8, 9. And so let me just add like a 0 x10 in here so I remember to delete it. Then I'm going to delete, and then I'm going to arrange. So you need to write it in order from my first variable to my last. I need to keep everything ordered, and every term needs to be there. So in this case, since there wasn't an x10 in that line, right, the coefficient is 0. Okay, so I'm making a matrix of my coefficients. I need to make sure every term is present in there. If a term isn't present in my equation as written, well, that just corresponds to having a coefficient of 0. So here I have x2, 3, 4, 5, 6, 7, 8, 9, 10. All right, I'm missing term 1. All right, so term 1 is going to have a coefficient of 0. And then I'll start with x2. Let me start by deleting, and then I will format. And so as I set up the matrix, since I have an open bracket, I can use a return instead of a semicolon for my next line. And this actually makes it nice and easy in terms of setting up, so I can see everything clearly formatted. Okay, so next line, x1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? We have all terms, so that's great. So I'm just going to go through and delete. Okay, then let's format. Bam. Okay, next x1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the right hand side, so all my terms are there. So I'm going to delete and then format like before. So that's good. Next one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Every term's there. Perfect. Okay, next one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there's my equality. Okay. Okay, next 1, 2, 3, 4, 5, 6. So I don't have x to the 7, so I'm going to have a 0 in here. X to the 7, 8, 9, 10, and then the equality. Perfect. Oh, sorry, I forgot. Hold on. Let me go through. I forgot to do my sanity check. Oh, so format that. So x2, 3, 4, 5, 6, 7, 8, 9, 10, and then the equality. So I'm going to need a 0 for the x1 term. Sorry, I was just in the zone of deleting, I guess. Bam. Okay, so I have my system of equations. Now the simplest way in terms of solving would just be, I'll say S is going to be rref, and I give it vector A. Okay, so I'm just going to play with this and we'll build it up. And so I'm going to call this exercise 8.3. Okay, so if I save it and then I run it, okay, yeah, so when I save it and I run it, so remember this first square part, all right? This is x1, 2, 3, 4, 5, so on and so forth. So if, what I'm looking for is when I put this in reduced row echelon form, I'm looking at the square part of the matrix, right? The first 10 rows and 10 columns. And I want just the diagonal elements to be 1, and then all of the off diagonals to be 0, which means I'm going to take this first equation and solve it for x1, second equation will be solved for x2, third equation will be solved for x3, and so on and so forth. And then the last column, right, is what x1 is equal to, x2, x3, and so on and so forth. Okay, so what I'm going to do is I'm going to suppress that output. Okay, so let me say solving. Okay, and then I'm going to say pulling out just the solution. And so I'm going to say my solution is going to be, if I look at S, and what I want from S is I want all rows, and I just want the last column, which is end. Okay. So if I clear my screen and now run it, okay, I just get a vector, and this is what x1 is solved for, x2, 3, 4, and so on and so forth. If I compare x1, negative 0.182, all right, so it looks like everything is good. Okay, so I successfully solved, right, my system of 10 equations with 10 unknowns, and then pulled out just the solution. Just a couple of other notes since we have this solved in the spirit of practicing for our exam is, if I have 10 equations with 10 unknowns, where we said, okay, that means I'm going to have one unique solution to my system of linear equations. Remember, formally though, it's if I have, n linearly independent equations, right? If I have n linearly independent equations and n unknowns, then there's going to be one unique solution. How I can determine the number of linearly independent equations is via the rank. Okay, so if I want to determine the number of linearly independent equations, well, then I want the rank, right? So it's going to be the rank, and I give it my matrix. So if I solve this, right, and run, I get a rank of 10, which means I have 10 linearly independent equations. Okay, and so, I could add a check, right? I could say maybe I'm checking the rank, minus the length of, so the length of, I'll look at, say, row 1, but I'm looking at, say, columns 1 through n minus 1, the second to last. All right, so if I look at one row, right, it's going to be the same for all the row, and I'm just looking at this subset of the matrix. So row 1 and then columns 1 through n minus 1 to second to last. The length of that would give me essentially the number of variables I have in my system of equations. Okay. Oop. 1 comma. Ooh, what did I do? Did I type this in right? Oh, So length of it's A, right? Then I'm pointing to that subset of A. I forgot the A part. Right? So now that ours is 0, right? And so I could add a logical check, right? And so I could say, if r equals 0, then display number of linearly independent equations equals number of unknowns. Else, maybe I display number of linearly independent equations not equal to number of unknowns. Okay, I could do something like that. All right, or if I were to wrap this in a function, right, I could make an error message, right? And so, hey, R0 number of linearly independent equations equals number of knowns, right? Perfect, proceed, right? And there's my solution, right? And you could do anything with this, but that's just an example of where I can use rank to check the number of linearly independent equations, and then check to make sure that's equal to the number of unknowns. And maybe I could use that to throw an error if it's a function, throw a warning, or anything of that nature. Okay, but there's my solution to problem 8.3. And you remember when I use rref, right? That's essentially you can think of it as an analytic solution. And so if I have a system of linear equations, using rref or left division is going to be preferred as compared to fsolve. But yeah, I guess just two other notes. All right, you can stop watching at this point. But if I want, this is a column vector. Okay, if I want a row vector, right, for some reason, maybe I'm working with row vectors. Remember how I would get that, as we call SOLR, right, is I would take the transpose, right, of that solution vector. Okay, so now I have my solution vector, right, as a column vector. Taking the transpose just converts it to a row vector if I was dealing with a row. And then the other way I could get the solution is via left division. And I guess I won't worry about it, right? Because I always use rref in class, but left division would be I'd create a subset of this matrix, maybe call that like B, make this a vector X, and then use left division to solve for the X's. But there's my solution. Let me know if you have any questions. If not, we'll see you in class.